Today I'm going to talk about the very long baseline interferometry or VLBI. VLBI is a method which is very much used in astronomy and also in geodesy for geodetic application, which is determining the baselines between the points which are very far from each other. The problem is that these VLBI stations, they needed to have big radio telescopes like this, big dishes, and maybe 30 meters, for example, the radius of 30 meters, to receive very big signals from the sky. So they can receive these signals for astronomical studies. Also, we can use these signals for geodetic studies that I'm going to talk about now today. So let's see that I have two VLBI stations at two points which are really far from each other. And I have some celestial objects which are quasars. That they will send this constant frequency continuously down to this. And since they are far from the Earth, then you can assume that the line of sight from the radio telescope to the quasars or the celestial object are parallel. If it is so, if signal comes to this point and the signal comes to this point, but they are not coming at the same time, they have a time difference. And why? Because they are coming, because this celestial object are very far from the Earth. And in that far distance, you can assume that they are parallel. Why they come faster to one than the another is because of the distance between these two stations, because of the distances. So if I plot a line like this here, which is perpendicular to this line coming from the quasar, this difference, let me call this tau, is tau. Tau is the delay that which is measured actually. But the question is how this can be related to the baseline. Baseline, what is a baseline? Baseline is a vector actually. Bx, by, and bz. So how this can be connected to this baseline? So if I have at this point, I have the coordinates of this. I wanted this vector actually. How can I get this vector? I say that, okay, I have the time difference. For example, if I have the atomic time here, let me clean this. Atomic time here, atomic clock and atomic clock here. And I measured this time difference. For example, I can measure how much when the signal comes to this radio telescope. 1, for example, when the signal comes to radio telescope 2. And it is the atomic time is measured and signal is registered at both. And what can we do? Here we have a correlator. What does a correlator? For example, the signal, let me see, at the station 1, we have here, and station 2 here. At the station 1, the signal comes like this. At station 2, the signal comes like this. And what the correlator does is to start comparing these two signals somehow to put them on each other, something like that. And move these signals backward and forward. Of course, I am talking very simple, but it's not that simple, the process. To find the maximum correlation between the signals. When it finds it done, then after that, they can find this remaining part and can measure this remaining. That's the principle. You have an atomic clocks at the stations. The signal is registered, the time is registered, and we can understand that how much the time difference is between these two stations. And later with the correlator, we will measure how much these two signals can interfere each other. We measure the interference. This is why we call this interferometry. We measure the interference pattern between these two signals. Then the signal delay can be computed. Then simply we can write a mathematical equation to determine, estimate the baseline. This time, which is here actually, which is the observable in VLBI, the measurements are this time entry. And I need to somehow connect this to the baseline, because this baseline Bx, By, and Bz are the things that I'm looking for. So let me call this one S. S is function of time. This S can be written as distance. We have S is this. We have the speed of the signal, equal to the speed of the light, over the time. In fact, this S is the distance, is because of the distance between the distance of the delay. How far, if this signal, for example, this signal from this celestial object comes to this time at the time t1, where it will be at time t, the time that it comes here. And this distance is the thing that we can find it from this tau. So if I solve tau from this, it will be 1 over, it will be S T over C. But that's not the thing that we want. We want this baseline. So if I have two vectors and I want to see projection of one to the other, what can I do? Then I perform inner product. Therefore, tau, let me write T, tau, the delay at time T will be the baseline, which I multiply inner products to ST divided by C. That's the principle of the VLBI.